Welcome to this lecture on internal model control design. We will present the design rules, we will present an example and Scilab code. Here is the schematic we studied in the previous video. The objective of IMC is to minimize error squared summed over an interval where E is given here. Recall that we saw GQ to be equal to GP inverse to get this y equals 0. So, in this lecture we will look at different methods to obtain this GQ by inverting the plant model. The reference for this topic is the book by Morari and Zafiriyu with details given here. First rule: invert the delay free plant model so that GQ is realizable. For example, if G equals z power minus k into B by A, then B by A inverse equals A by B is a candidate for GQ. We assume that all the delay is factored into this z power minus k. The second design rule is given now. If the plant is non-minimum phase, then replace the non-Hurwitz factors, that is the factors with zeros outside the unit circle, with reciprocal polynomials. That is, if G is given here, then the candidate for GQ is only the delay less part is inverted. In addition, we change the order of the polynomials. So, it starts with z minus and it becomes a constant term here. More details on the reciprocal polynomial given in the textbook. So, as a result it becomes A divided by minus 2 plus z inverse. The 0 of the plant is at 2. You can see that the 0 of the plant to be 2, whereas that of the pole of GQ is 1 by 2, that is equal to 0.5. So, the reciprocal polynomial is easily obtained. Just given polynomial has to be factored into first degree polynomial and replace the zeros of non-Hurwitz factors with their reciprocals. The third design rule is given here. If the plant 0 has negative real part, replace that part with steady state equivalent. For example, if the plant is given here, then the plant has a 0 at minus 0.5. Then the candidate for GQ is the reciprocal of this, with this part being replaced by its steady state equivalent. Can you guess why we are doing this? This is because if you do not do this, if a factor minus 0.5 is here, then this will result in large oscillations in the control effort. This is something we have already seen while discussing pole placement controllers. So, in this particular case, when I substitute z equals 1, I get A by 1.5. And there is one more rule. The noise and model mismatch have mainly high frequency components. To account for these, a low pass filter of the form BF by AF, which can be given in the form of 1 minus alpha by 1 minus alpha z inverse, where alpha is in the range 0 to 1. Recall the pole 0 location based filters that we studied earlier. If you go through that discussion, you will see that this is a low pass filter. This filter is added in series. So let me summarize. The Planck transfer function is factored as given here, where Bg is the factor of B with roots inside the unit circle and with positive real parts. B minus is the factor of B with roots that have negative real parts. Note that these roots can be inside, on or outside the unit circle. Bnm plus refers to that part of B containing non-minimum zeros of B with positive real parts. It will become clear in the next slide. The Planck transfer function is factored as given here. Here is the drawing of it. Here is Bg, this is inside the unit circle with positive real part. Nm plus is outside the unit circle with positive real part, and B minus has negative real part. Whether it is inside the unit circle or outside the unit circle does not matter. So with this plant, IMC is given by GQ equals G pseudo inverse times GF, where pseudo inverse is given here, where Bs minus is the steady state equivalent of B minus, this is for the negative part, and Br Nm plus is Bnm plus with reversed coefficients, that is Bnm plus, its coefficient has to be reversed. We will explain this with an example. The transfer function for this is given here, where the time unit is minutes. We will sample this with Ts equals 0.1 minute. We arrive at this discrete time transfer function, and A is the denominator and B is the numerator. You can see that this factor has a 0 outside the unit circle, so it is non-minimum phase. This is Bg, it is a constant, so we can retain it as it is, and B minus equals 1, there is no B minus. So this is the one that has to be replaced with its reciprocal, so we get this polynomial. Up to this is what we saw earlier, namely Br Nm plus is the reciprocal polynomial, we got Bg and B minus. Now the controller is obtained as the reciprocal of this all except this Z inverse. So what is in the denominator goes to the numerator, and in the place of this we replace it with the reciprocal polynomial here into GF, that is the low pass filter, which is written as 1 minus alpha into 1 minus alpha Z inverse. Remember, in this approach we need only a first order filter as given here. We will never have the case of numerator degree being greater than that of the denominator degree, as it may happen in continuous domain transfer function, because in discrete time we use polynomials in Z inverse. We will next implement this in Scilab. This file is called VANDE underscore imc1.sce. In this I invoke this file imc underscore stable1, which is listed here, and that uses imc split.sci, it is given here, and we use this flip to get the non-minimum phase reciprocal. Here is imc split.sci, and after executing that you design controller, then Using this file, we set up XCOS simulation, which also starts the simulation. So, if you execute this, you will automatically get this XCOS file opening and this output appearing. Of course, you will not get both of them, you will have to do this twice to get two simulation outputs. Solid lines correspond to alpha equals 0.5 and dotted lines correspond to alpha equals 0.9. This is the plant output, this is the control effort. You can see that for alpha equals 0.9, the response is slower, but the inverse response is also smaller. When it becomes negative and becomes positive, this is known as inverse response. You can see that when the system is made slower, the inverse response also is smaller. To conclude, the internal model control is an elegant idea. Controller search needs to be done only amongst stable plants. Although unstable plants can be handled, one generally uses this method for stable plants only. IMC based tuning methods are very popular amongst chemical engineers. Details are in the textbook. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.